Right now, you are sitting still. Or at least, you think you are. But deep inside your skull, there is a tiny system running constantly, tracking every tilt, every turn, every micro-shift of your head. And it has been doing this since before you were born. Most of the time, it works perfectly. You never notice it. But spin around 10 times in a circle, and suddenly the world won't stop moving, even after you do. The floor tilts. Your stomach lurches. Your eyes flicker side to side like something is broken. And you didn't hit your head. You didn't take any medication. You just spun in a circle. So why does your body fall apart so completely from something so simple? The real answer is far stranger than you think. Because dizziness isn't a malfunction. It's your brain catching you in a lie. Your body uses 3 completely separate systems to figure out where it is in space. The first is your vision. Your eyes scan the world and send signals to your brain about which way is up, which way is down, what's moving, what's still. The second is something called proprioception, the ability of your muscles, joints, and skin to sense the position of your own body parts without looking at them. Close your eyes and touch your nose. That's proprioception. It's the reason you don't fall over every time you blink. The third system is the one that causes all the trouble. It lives inside your inner ear, and it is ancient. Deep inside each of your ears, tucked behind the eardrum and the cochlea, the spiral shell-shaped organ responsible for hearing, there is a structure called the vestibular system. The word comes from the Latin vestibulum, meaning entrance hall. Think of it as the lobby of your brain's navigation center. Inside this system are 2 types of sensors. The first type is called the otolith organs, 2 small chambers lined with tiny hair cells, covered in a gel containing microscopic crystals made of calcium carbonate. When your head tilts or accelerates in a straight line, those crystals shift, bending the hair cells, which fire electrical signals to your brain. This is how your body detects gravity and linear movement, walking forward, falling, riding in a car. The second type is the one that dizziness lives in. They are called the semicircular canals. You have 3 of them in each ear, arranged at right angles to each other, one horizontal, one angled forward, one angled backward. Each canal is a hollow loop filled with fluid called endolymph, and at the base of each loop sits a tiny cluster of hair cells topped with a gelatinous dome called the cupula. When you rotate your head, the fluid inside the canal doesn't move instantly with your skull. It lags behind, like coffee sloshing in a mug when you spin the mug suddenly. That lag pushes against the cupula, bending the hair cells, which again fire signals to your brain. 3 canals, 3 axes of rotation. Your brain receives data from all 6 canals simultaneously, 3 in each ear, and triangulates your exact rotational position in 3-dimensional space. This system is extraordinarily precise. Researcher David Angelaki at Baylor College of Medicine has spent years mapping how the vestibular system processes motion signals, and her findings reveal just how computationally sophisticated this tiny organ is. It doesn't just detect motion, it predicts it. It builds a running model of your movement trajectory and uses that model to stabilize your vision, coordinate your balance, and keep your body upright, all without you thinking about it for even a single second. Now here is where spinning breaks everything. When you start spinning, the endolymph in your semicircular canals begins to lag behind your skull. Your hair cells bend. Your brain reads the signal correctly. You are rotating. But keep spinning at a steady speed for more than a few seconds, and something subtle happens. The fluid catches up. The endolymph accelerates to match the rotation of your skull, which means it is no longer lagging. Which means the cupula is no longer being deflected. Which means the hair cells are no longer bending. Which means your vestibular system stops detecting the rotation entirely, even though you're still spinning just as fast as before. Your eyes, meanwhile, have drifted. They are still trying to compensate for the rotation through a reflex called the vestibulo-ocular reflex. This reflex is one of the fastest in the human body. It works by taking the motion signal from your vestibular system and using it to drive your eyes in the opposite direction, so that even as your head moves, your visual field stays stable. It's the reason you can read a sign while nodding your head. It's the reason surgeons can lean over a patient without their vision blurring. But while you are spinning at a constant speed, this reflex is receiving diminished signals, so it partially disengages. Your vision adjusts. Your brain updates its internal model. You are now still. Then you stop. The moment your body halts, the endolymph does not stop immediately. It keeps flowing, carried by inertia, in the direction you were spinning. The fluid surges against the cupula again. the hair cells bend. But this time, they are bending in the direction that signals the opposite rotation from what actually happened. Your vestibular system fires a signal that says, you are now spinning in the other direction. At the same time, your eyes receive this false signal, and the vestibulo-ocular reflex kicks back in, driving your eyes rapidly in the direction of the phantom spin before snapping back. This involuntary eye movement has a name, nystagmus. It is the flickering, darting eye motion you can sometimes see in someone who has just stepped off a spinning chair or a merry-go-round. Now your brain is receiving three completely contradictory reports. Your vestibular system says you are rotating. Your eyes are locked onto a stationary room that says you are not. Your proprioceptive system, your muscles and joints, says you are standing still. Three inputs, three different answers, and your brain cannot reconcile them. Researcher Kathleen Cullen at Johns Hopkins University has studied what she calls the neural conflict model of dizziness, the idea that vertigo is not the result of damage to any one system, but of the mismatch between predicted and actual sensory signals. When your brain's internal prediction model says you should be still, but your inner ear insists you are moving, the brain treats that conflict as a crisis. Something is deeply wrong, and it has a few pre-programmed emergency responses. Nausea is one of them. This might seem strange. What does spinning have to do with your stomach? But evolutionary biologist Dr. Michael Treisman proposed decades ago that motion sickness and vomiting are ancient protective responses triggered specifically by sensory conflict. In the ancient world, the most common cause of visual and vestibular signals contradicting each other was not a merry-go-round, it was neurotoxic poisoning. Certain plant toxins and bacterial infections can disrupt the central nervous system in ways that scramble sensory processing. When your brain detects that your eyes and your inner ear disagree about reality, it does not conclude that you have been spinning. It concludes, based on millions of years of evolutionary wiring, that you may have ingested something dangerous. And the fastest way to deal with ingested poison is to expel the contents of your stomach. Your nausea after spinning is, in a very real sense, an ancient misfire. Your brain is trying to save your life from a threat that does not exist. The dizziness itself, the sensation that the room is rotating, is your brain's best attempt to make sense of the contradictory data. Rather than simply report uncertainty, your brain picks the strongest signal and constructs a coherent story around it. The vestibular signal says rotation, so the room rotates. The fact that your eyes can see perfectly well that the room is stationary doesn't override the signal, it amplifies the confusion. Two systems screaming two different things simultaneously. And your brain, caught in the middle, flickers between both realities, which is what produces that unsettling, unmoored feeling that you cannot simply choose to stop. Children spin in circles on purpose. They chase this feeling. They throw themselves into it, arms out, heads back, laughing until they collapse. And there is a reason for that. Vestibular stimulation of a certain intensity produces a mild euphoric response, a kind of sensory flooding that activates reward circuits. Researcher Alain Berthoz at the Collège de France has written extensively about how the vestibular system does not just process motion. It is deeply connected to emotional processing centers in the brain, including areas involved in spatial memory, fear, and pleasure. The feeling of spinning, of controlled disorientation, lights up pathways that are also activated by other intense physical experiences. It is not an accident that roller coasters exist, or that dance involves spinning, or that certain meditation practices deliberately induce rotational movement. Your inner ear is wired to your brain in ways that go far beyond simple balance. The sensitivity of this system also explains why some people suffer from a condition called benign paroxysmal positional vertigo, BPPV for short. In this condition, one of those tiny calcium carbonate crystals in the otolith organs breaks loose and drifts into one of the semicircular canals. When that person tilts their head in a certain direction, the rogue crystal rolls through the canal, deflecting the cupula and sending a false rotation signal to the brain. The result is sudden, violent vertigo, sometimes intense enough to cause falls, triggered by nothing more than rolling over in bed or tilting the head to look upward. The room spins without warning, from a fragment of crystal smaller than a grain of sand. And a trained clinician can cure it in minutes by guiding the patient through a specific sequence of head positions called the Epley maneuver essentially using gravity to herd the crystal back to where it belongs. One of the most dramatic symptoms in medicine, resolved by careful, deliberate tilting of the head. That ancient system inside your ears has been calibrating reality for your entire life, every step you have taken without falling, every time you have caught yourself before stumbling, every time you read something in a moving car without losing the page. That was your semicircular canals and your otolith organs and a vast web of neural circuits, all working in concert, faster than conscious thought, modeling the physical world and keeping you upright inside it. So tonight, if you spin your chair too fast, or stand up too quickly, or just feel briefly unmoored for a moment you can't quite explain, that is not your body glitching. That is 300 million years of vertebrate evolution, running a system so complex that scientists are still mapping it, catching a single small inconsistency in the story your senses are telling, and doing what brains have always done, trying to decide what is real, just like it did the first time you ever sat down and felt completely still.